Open. Open. Right. First question. Right, give an example of something which is stable. Yeah. Whatever. Stable. No. Stable means no, not a seesaw or chair.
Triangle.
No. Well, no. I'm thinking more. I want the center of gravity to be below the turning point, so that if you knock it, it will just go back. Pendulum, a clock, yeah, something like this. Something which is neutral. Oh, sorry, unstable. Bottle of water. You can easily knock it. Okay. And then what's something neutral? Well, something neutral would be seesaw. Something balanced like this, for example. No, wait. Where the center of gravity is at the turning point. This is neutral. Seesaw will do, yeah. Okay. Right. Okay. So we really just care about question 4. Yes? No, come on. Right. A boy and his father goes to the park. The boy is 40 kilograms and the father is 100 kilograms. So these are big people. A boy sits on a swing which is 3 meters long and his father pushes him with a force of 100. What is the moment of this force? So what's happening in the first part? The boy is sitting on the swing. There's the boy. And the father pushes him with a force of 100 newtons. And this is 3 meters long. So the turning force is 300 Newton meters. Okay. Is that okay? If the boy and father swaps places and the boy tries to push his father with 100 newtons of force, how much moment is being applied now? So what I want you to see is that even if it's the father and the boy with 100 newtons, the turning force is still the same, because all you care about is the distance here and the force. You don't care about the mass here. It's not important. So it's still 300 Newton meters. Yeah? Now, this isn't realistic because the reason it's more difficult for the boy, it's not because the father's heavy. The reason it's more difficult for the boy is because his force he will push at will be less than 100. Okay? But it's not important about the mass of the person on the swing. Well, the force is still 100, and the rope is still 3 meters, so it's still 300. Now, in a real example, the boy is not as strong as the man, so it will be less than 100. But the point I'm making is that you don't care about the mass here. So if you look at the door, look, if I pull with this force here, 100 newtons, yep, and this distance here is say 1 meter, I don't care about the mass of the door. It's not important for my calculation. I only care about this force and this distance. Not the mass of the door. It's not important for this calculation. Okay. So that was the point I was making with the B part. Okay, the C part. The boy is now on a seesaw by himself. The seesaw is 5 meters long. What is the moment? Okay. So in part C, here is the seesaw, and here is the boy.
and he is 40 kilograms. So when he sits here, what will happen? It will want to turn this way. The turning force, what's the distance here?
2.5.
Very good, 2.5, because it's only from here to here. And what's the force?
2.5 times 40.
Yeah, the force is his weight.
No, it's 2.5 times 40 times
Yeah, times
10.
40 G.
Yeah.
So that would be 2.5 times 40 times 9.81. So this is 981 newtons.
How are you calculating this 2.5 distance?
The question said the seesaw is 5 meters long.
Oh, I see.
Yeah, so I have to half it. Okay. What's wrong, Grace? Are you sure? Okay. If the father is on the other end, what's his turning force? So now if the father sits here,
It's the same.
no, it's not here because his weight is bigger.
I thought the weight didn't matter.
The mass doesn't matter, but the weight is what is the force here.
Earlier was a vertical thing.
Yeah, yeah. So for D, it will be 2.5 times 100 G, which will be a lot bigger.
2,000.
Yeah, 2452.5 newtons for part D. Yeah. Okay. E, the father will apply more turning force than the boy. How much more?
Minus.
Yeah, so can I go down a bit? E. So what's happening here is that the boy has a turning force this way of 981 newtons, and the father has a turning force this way of 2452.5 newtons. So in total, that's like just one force this way of 2452.5 minus 981. Two, 4, 5, 2.5. So that is like 147, 1.5 sorry, not Newton meters, of course. Newton meters. So no surprise that the swing will move that way. The seesaw. Okay. And F. Okay, can I do the last part? Yeah. So for the last part, what happens? So I have a very nice little story here. The father and the son sit on the swing together. So their mass is 140 kilograms together. This distance here is still 3 meters. And I tell you that this angle here is 30 degrees. So what I'll do is I'll just make a little triangle here. So this is 90. So what's this angle here, please? What's
160.
no, 60. Yep. Sorry, it's a bit hard to see. Let me just try and fill that in. 60. I don't want it too dark. 30. Okay. So what is the turning force now? So the force here is the weight, which is 140 G, which is newtons. So the turning force is something multiplied by something. Okay. Now, I need to go to the side for one moment to show you something. So look over here. Imagine I have the force like this. What you could do is break the force up into a piece this way and a piece this way. So then the turning force would be this distance multiplied. Oh, Grace, you're not looking. Why aren't you looking? And now I'm going to start again. Right, so this here is L, and this here is W. So I could break this up into a piece this way and this way. So the turning force would be this distance multiplied by this force. Why don't I use this one?
Because force will be perpendicular force.
Yes, that's it. In the definition, it must be the perpendicular force. Now, there are other ways to think about it, but this is the easiest way to think about it, so we'll just do it this way. I know you don't need this diagram, you really need this one. So what we'll do is we'll break this up into this direction and into this one. So it'll be 3 multiplied by this one. And this will be 1373.4 cos or sine. What do you think? Well, if this is 30 and this is 60, maybe you can see that this one here is 30 also? That this angle is the same as this angle?
Yeah.
So this is 30. So this, will it be cos or sine 30?
It will be cos, because it's not opposite.
It'll be sine 30.
What? I thought only if it's opposite.
No, no.
sine.
The trick I gave at the start of the year, which I think you missed then, is that cos is the one that touches the angle and sine is the other one.
Yeah, but isn't it touching?
No, no. This one is touching the angle. This one does not have the angle.
But it's the same, isn't it also 30?
No, it is not. This one here is actually 60
Oh.
because this is 90 altogether.
Okay.
Yeah. Because this is actually opposite for this triangle. Anyway, times sine 30, and you get 686.7. So the answer is 2060 Newton meters.
How you use this 30, this one? Like, you're taking this force.
Yeah, how is it 30? Or how did I use the 30?
Yeah, like, how is 30?
Well, what we're doing here, well, oh, how is it 30? Yeah, there's a theorem in maths which says that if you have 2 parallel lines, the angle here is the same as the angle here. So that's actually what you have here. There's one line, and then there's this line, and then there's a line that goes through them. So this angle here is the same as this angle here. So that's why that's 30.
So this 30 angle is the angle between weight, which is downward?
Yep, and the component which is in the same direction as the string, and this component is perpendicular. What we're doing is, I don't know if you know this word, we're resolving the vector into 2 other vectors which are perpendicular. So one of them will be a cos and the other one will be a sine. Yeah. So the trick I gave at the start of the year was the one that touches the angle is the cos. Okay. Have you got that written down? Yeah. In this picture here, this one is the sine and this one is the cos, yeah.
Like angles between these two, so it is cos and the other one is sine.
Yeah, this one is the cos and if you wanted this one, I needed the sine. If I wanted this, I don't need this one, but if I wanted it, it would be this multiply cos 30.
Cos 30.
Yeah. Okay. I can close this? I can close it?
Yeah.
One sec.
Yeah, now.
Okay. Closing.